if I were a rich man. All day long I'd biddy bum if I were a wealthy man. Wouldn't have to work hard.
A couple of quick announcements about the class. To make up for some of the time we're losing thanks to technical difficulties, and to also supplement your learning, we are going to be providing, cameras over here. We are going to be providing some supplementary videos online to explore certain aspects of the course. The first one of these is already uploaded. It is on the Find Repeats material that we covered last week, exploring how we can make the Find Repeats algorithm even faster, as well as providing a more complete and clearer analysis of the suffix array runtime. So go ahead, check that out. There'll be another module coming out hopefully this week with basic C programs, switch statements, and a walkthrough of some of the material we've covered, at least in theory so far, and that you'll be doing in workshops. So today, if any of you can guess from this picture, we are studying loops, for loops and while loops. And there do exist do-while loops, but we encourage you to stay away from them, even if you find out about them in the textbook. They don't function any better than the regular while ones, and their uses are a little bit obscure. So why do we use loops? Well, all of you are familiar with it at this point from your prior classes, but loops enable iteration. If we have a large set of items, and potentially we might not even know ahead of time how many items there are, instead of copying out our code multiple times in order to perform the same operation again and again, we abstract this away and use a loop. We tell the computer to repeat the same action with the internal contents on what we're performing the action, changing with each time, changing with each iteration. This is the structure of a for loop in C, and we're going to check this out in actual code, but we'll follow along with the graphic in the meantime. And on the recording, we're going to have that annoying bar again until the X is pressed. Liam, do you want to fix that? X. Okay, so at the very start, in our for syntax in C, we have a statement called the initialization statement. Before anything else in the loop runs, you get a chance to tell the compiler that you want it to run this little bit of code to set up the loop. So for example, if we have a counter in our loop that we want to start at 0 or that we want to start at 2, that's what you would put in the initialization. Oh,
it's my fault.
No worries.
There's no mouse.
There is no mouse. Then after initialization, you have the first instance of the condition. The condition is what you're going to check with each iteration of the loop to make sure that you should still stay in the loop. If the condition is evaluated to be false, you proceed no further. You don't even run the loop once. If the condition is true, we go to step 3, which is over here. Step 3, step 4, we go into step 3, if true, we go into number 4, the body of the loop. We run some commands, whatever is in the block. So this is within the square, within the parentheses, the curly braces. Or if you're using the go-to-fail style of programming, the next line with a colon on it, we run those, and then we go back to, step 5 is mysteriously missing, but we go back and, there it is, step 5, we go up here and we go and run the update statement. Now the update statement should change the state of the variables in the program such that eventually, it doesn't have to be the first time you run it, but eventually when you get back to the condition in the next step, one of these times the condition should evaluate to false and we should end the loop. If at no point in time, either in the body or in your update statement, do you make any impact on the condition, you'll get an infinite loop and you won't actually be able to terminate your program. Okay, now we've got some live coding anyway, so this might give us another chance to
do the duplicate display, and then you'll be able to actually close it now. Good.
Except the mouse is gone again.
Close the keyboard for a sec. There you go.
Yeah. Now, is the transcript thing still there? No. Okay, let's bring up our trusty terminal, and let's write our very first loop. Okay, there we go, line 1. So we'll have our usual standard I/O so that we can actually get input in and out of our program. Our main function. And let's try a basic loop in 2 variants. So this is one variant. Oh, let's leave it at int I equals 0, I less than 10, I plus plus. So does someone want to tell me what this loop is going to do? You can probably already see what I'm writing. That's it. Someone from the audience, what does this loop do really fast? Yep, prints 1 to 9 without a new line. Let's see if that works. Loop. Okay, there we go. Our number's 0 to 9. Sorry, 0 to 9, not 1 to 9, because we started at 0. And remember the order of things that happens, we run our initialization, we run our condition, and then we go into the loop body. It's not until after the loop body has already run for the first time that we get to our update statement and we get to the loop check again. Now here's another way of writing the same thing. Let's see if this one works. Now I have a blank statement in the initialization. Will our code still work? Let's give it a try. Still works. Okay, so that teaches us something. These statements can be blank. Now what about if I do that? Will that still work? Yes or no? No. Why not? Okay, Shinjiang, you're going to have to stop answering for a bit so other people in the class can get to it as well. Why won't it work? Anyone else? Yeah. I is not initialized, but this doesn't necessarily mean our code won't work. Let's see what happens when we run it. That's a bit of a mystery. What about if we try printing I at this point? What do you think we'll see? So let's give it a run. That's a little strange. I still has a value. This is kind of curious. We haven't initialized I, and yet it already has something inside it. Let's give it another run. It might be different this time. Yeah, and different again, different again. One of the things that you're doing when you initialize a variable is telling the computer which block of memory to set aside for the variable. What you're not doing is telling it what to put in there. When your program ends, the memory doesn't get destroyed. There's no fire inside your computer's hard drive. The memory is still there, which means that another program might use it, might fill it up with something different. And then when you run your program and initialize a variable and it gets that block again, that block might still have things in it. The computer doesn't automatically set it to 0, it just leaves it as is. And this can be a major source of bugs in your code. If you don't initialize something and you don't have all the fancy compiler flags set, you might not even notice, and then you'll get these strange results because your variables might take on the value 0, but they could also take on any other value that could have been stored in the computer's memory. And display settings. Sorry, we've got to figure out how to get back into the other mode. There we go. Stop mirroring. There we go. Okay. So there's another example of our syntax. This is a different loop that we coded up earlier. In this case, we have something called continue. The continue keyword is built into the C programming language, and what it allows us to do is it allows us to get out of a loop early. So from step 4, running the code's body, if we want to go immediately back up to the update step and then to the condition step again, we can skip the rest of the body of the loop with the continue statement. So any ideas what this one will print? Yara, do you want to turn on the microphone and give it to someone? Any idea what this code is going to print? Over there. And I don't remember your name, so you'll have to remind me.
My name's Evan, and
Evan.
It'll print 0, 1, 2,
and then 4.
Exactly. So in this case, we're going to skip when I is equal to 3. We'll go from that point back to the update statement. We'll increase I by 1 again, and then eventually we'll exit the loop. We're still making progress. It doesn't end the loop entirely. It just skips the rest of the loop body. One thing that we're going to focus pretty heavily on in this course that you won't have seen in Foundations of Computing is a loop invariant. This is something that is always true, that we can say is always going to be true in the loop body. Now, loop invariants are not true because the compiler enforces them. They're true because of the way that you are going to design your code so that you know at every stage when you're running your program, the thing inside the loop is going to stay true, some statement is going to stay true, which will allow you to prove things about your broader program. So let's go back a step and go to this loop. What might a loop invariant be? What thing is always going to be true while we're running our loop? And it should be something intelligently connected to the loop. Yeah. I is an integer, so that's a reasonable invariant. They've got to stay far apart or they'll interfere, or they can be off. I is an integer. Yes, that's always true, but that's not going to tell us anything useful about the progress the loop is making. Your name was Evan, right? No? No, further back. I've forgotten your name in the red t-shirt. We spoke before. Yes? What was your name again? Marlo. Got it, sorry.
Well, you've defined, it's not in the loop, but you've defined like I as 0 before start of the loop. This isn't exactly this question, but if that was in the initialization, then that's something that you'd have invariant.
So I is not always going to be equal to 0. Yara, stay with the microphone for a second for Marlo. What is going to be true about I, though? There is something that we can say even when the loop is over that's still true.
Would that be the memory that you've allocated it?
So let's look at our condition over here. We know that while we're inside the loop, I is always less than 5. So that's our invariant in this case. It's a really simple invariant, and it's the same as our condition. However, it still remains true. Thanks. Yeah, we're good. So once we get to more complex loops, the condition and the invariant are not always going to stay the same. Also, I misspoke. It's not true after the end of the loop. It's true while we're in the loop. We're going to use the point at which it becomes false in order to prove things about our program. And we'll see some more sophisticated invariants soon. So an invariant should always be satisfied by the initialization. In this case, when we set I equal to 0, we should also be able to make the statement at the same time that the invariant is true as a result of the initialization. So setting I to 0 proves to us that I is less than 5. Very trivial, but it's going to become important because that provides us a starting place with which to base our proof on the algorithm's behavior. On subsequent iterations, there should always be a change. We should be making progress towards the invariant becoming false, because if it always stayed true, the loop would keep running. And so eventually, through the iterations, our invariant should be false. When the guard is false, some outcome should have been achieved. So for example, if we know that in each iteration of the loop, we're printing the current number, and we know that the loop invariant is always going to be true until I has gotten to 5, we know that, and we know by induction, that each of the numbers between 0 and 5 are going to be printed, and that no numbers larger are going to be printed. And this seems like a very trivial proof, but it's going to be the same sort of structure that we'll use to prove more complex things. One pro tip that I'm going to give to you for free is try and start your loops at 0 with your counter. This is, it's tempting to one-index things, but because many other things in C are 0 indexed, such as arrays, which we'll talk about next week, if you start your loops at 1, it will be a lot harder to keep track of the relationship between the other objects in your C program and your loop counter. We have a few more odds and ends before we return to some sample programs. One thing is that just by standard, by agreement between C programmers and the C manual for the C libraries, when a function fails, such as printf or scanf, it should give us a predictable return value. And that predictable return value should be 0 for success, or in some cases, the amount that it succeeded. For example, if you're using scanf and you try and read in 3 things, it should give you the number of things successfully read, and you can find that out in the man pages. But if it's failed, most library functions should return -1 or some negative number depending on the code. In the vast majority of cases, this will just be a straight -1, but in some other cases, you might have to check the man page for any exceptions to this rule. This gives us an easy way of checking whether what we're doing has actually succeeded. Here is an example with scanf. Oh, that stupid zoom bar is at the top again. It'll be impossible to remove. Okay, we'll just have to leave it and I'll go back and edit it out after. So in this case, we're checking to see if scanf has succeeded. We're trying to read in 3 things. And we know that if it hasn't read in 3 things, then something has gone wrong. The return value won't be 3, and we can print out that scanf failed. This becomes important when debugging your program because you won't always know why or where your program is failing. For example, if you run scanf, it doesn't succeed, but you let your computer keep running, these variables might still go uninitialized, and you'll get that same weird behavior that we had earlier. Another thing that we'll talk about in terms of improving the quality of your code is special casing. In this instance, special casing is actually legitimate. What do I mean by special casing? I mean when you have values and a selection that is occurring in your program that selects for very specific or unusual events. In this case, years, days, and months, the number of days in each, don't follow some obvious pattern because this was a human design by Augustus Caesar and Julius Caesar. The number of days in a year, and the number of days in a month does not necessarily make total sense. And because C and mathematics don't have an inbuilt sense of the planet Earth's specialness, there's no inbuilt notion of the number of days in a year on planet Earth, nor the amount that we have to make up for the difference that occurs in the number of days in a year as a result of leap years. So this is where a special case is actually useful. Days in a month, days in a year, months in a year, these kinds of things that are not inherent to the actual structure of the algorithm or the problem we're looking at, but are really something that comes from outside. However, when you have a special case in your code that is like when the loop equals 1, when the loop equals 2, when the loop equals 3 with if statements, that's an indication of inappropriate special casing. And so one thing that we're going to be looking out for in your code this year is instances where you've done special casing correctly, which will be uncommon, in special casing incorrectly, which should be uncommon, and cases where you've used it correctly where absolutely necessary. So here you'll see further special casing. We have if the month is 2, so that would be February, the length of the month is 28 days. So 30 days have September, April, June, and November, all the rest of 31 except February. This is an example of an acceptable special case. One thing I'll point out to you here is the special double bar operator that we're using. Does anyone know what that is? Someone who's perhaps read a little further in the book? Yeah, it's the OR operator. The OR operator allows us to make logical disjunctions between statements. So either that is true, or that is true, or that is true, or that is true. The double bar has to separate them all. One thing I will note, and we'll actually go into the terminal quickly to show this. And I will come up with an example very quickly. That's not what I wanted to do. This is not valid C syntax. You actually the ORs separate out evaluations that are complete in themselves. So this might actually compile. We can see. But firstly, there's an error there. And secondly, that should be like that. However, we can give it a run and see what happens. I actually don't know. And this is one of the beautiful things about programming in C. I forgot a semicolon as well. I'll go back and put that in. Where did I forget a semicolon? Oh, up there. Okay, so it didn't even compile in this case. Extraneous closing brace. Oh, it probably wants some statement in the middle because of the compiler options. Extraneous closing brace still. Okay. I can't see the error in my code off the top of my head. Oh, it's probably just realizing that my syntax is all, there's an extra brace there. Okay, I've screwed up my terminal. There we go, it actually compiles now. So it's still running the hello, and in this case, why is it running? Why is it actually running even though this isn't valid C? Or is valid C, but definitely doesn't do what we wanted it to do. Yara, you're on the mic again. Why did it print hello world even though B is equal to 2? Want to run it down here? Yara, over here. This guy over here. Remind me your name again.
Yes, hi, Vincent.
Vincent.
Yes. Right. It's because an integer value one is like it has like truth-like property.
Exactly. So remember last lecture we were talking about truthiness. A is a non-zero value. It's 1. Therefore, it's truthy. Therefore, this is 1 or B equals 1. And at least the left side of that is true, even though the right side isn't true. And so our OR statement still evaluates to true, and it prints hello world. Wasn't sure if the compiler would allow me to do that, but evidently it does. Okay, we have a whole bunch of demos for much of the rest of today's lecture. And for the ones we don't make, I will upload onto the LMS so that you can get a hands-on experience with a few more programming examples. This will be a pattern for some of our lectures, at least in the early stages. Once we've covered some important concepts in the programming language, we'll go back, look at some actual real code, just to give you a sense of what's going on. And then hopefully, if all goes well, Liam will upload a lecture on the C programming language to cover for all the bits and pieces that we can't get to in class. So let's look at the first program in this list. I guess it's not in here. Okay. So this is the program that we just saw broken up into pieces. We start with initializing day, month, year, and then we have all our special cases in here. So length of February is 28 plus the year percentage sign for. What are we using the percentage sign for here? What do we know about leap years? What was that? Yeah, it's remainder. What do we know about leap years though? When do leap years happen?
February.
Well, that tells us when our leap day happens. How frequently do leap years happen?
Every 4 years.
Every 4 years
that's right,
in the normal instance, but every 100 years, the 4th year is not a leap year. And every 400 years, every 100 years, it's a leap year again, and every 400 years, again, despite the deviation. And so in this case, we've had to special case for all of these instances because of the structure of the Earth going around the sun doesn't neatly fit into a nice pattern of iteration. So we've got that there again. Okay, you see we've also got 30 days, hate September, April, June, November. All of these have 30, except for the rest, which have 31 alone. And at the end of the day, we're just trying to print what day number we are in the year. So figure out what month number we're up to, add together all the number of days in all of the months prior, and then once you're at the current month, just add how many days into it you are. So for example, if we're in the month of January, we don't need to know how many days January has, as long as we are less than the number of days in January. So if the date is the 7th of January, we know we're 7 days into the year. However, if the date that's being given is the 1st of February, we need to now count all the days in January plus 1 day into February. Or if the month is March, all the days in January, all the days in February, and then however many days we are into March. So that's what this program does. Let's give it a run. Okay, what date should I put in? Today. Okay, what is the date today? It is the 9th of March, 2022. And it is day number 68 in the year. Great. Okay, next demo. Let's see, maybe I'll make this a little smaller so we can see more code at once. That's still readable. Okay, what we have here is the first nested for loop of our semester. All of you will have seen these somewhere in your programming journey before, but this shows us how to combine them in an interesting way. So the first thing we're doing is we have an outer for loop with a counter I, and this is using a hash defined, some magic number that we're declaring up at the top of our program, because we don't want to have all these random numbers in various different places in our program. So from I is 0 to 5, we're going to increment I each time, and then for each time we do that, we're going to do something else. In this instance, starting on line 11, for each iteration of I, we're going to run the initialization, so set j equal to 0, run the check, is j less than I? Well, we know that if this is going to be a loop invariant and a condition, it should be trivially satisfied, so j should always be less than I, except when is 0 not going to be less than I? Is 0 less than 0? No, so that is something to watch out for, is whether it is greater than or equal to. Be very careful with those, another common C programming error. And for each of those, so until we get up to the point where j is equal to what the value of I currently is, print the value of I, print the value of j, and then a new line. Let's see what this does. For loop 2. And you can see that we've skipped the case where I equals 0 and where j equals 0, and we've moved on immediately to where I equals 1 and j equals 0. But we don't have a case for I equals 1, j equals 1, because in that case, I is not greater than j when they're both the same number. And so we have 1, 2, 3, 4 items on each successive line, illustrating that you can combine loops within each other to do more sophisticated forms of iteration. Okay, great. Nothing particularly new so far. The only different thing from hopefully what you already know is the C syntax. Let's step it up a notch. Okay, any idea what this one does? We'll take this one from the audience. Any takers? And there's a chocolate for this one too. Yash. He's already got it. It's fine. You can take a seat. So in this case, we are multiplying I by 10 over and over and over until we get to that large number. I can't see how many zeros. 6, 7, 8, 9 zeros. So 10 to the power of 9. But we're starting from I equals 3. Then we print I again, and then we print I squared. Let's see what it does. Maybe that'll give us a little more insight into what's going on here. For loop 3. So it's produced a beautiful triangle of our increasing powers of 10 of 3, and it's producing like a nice little pyramid thing. So let's go back to the code and look at how it did that. So here we have more sophisticated format specifiers that are printing a given number of spaces for each of the subsequent lines. The way we're doing this is using alignment, and Liam, I think, might cover in his C lecture format specifiers and alignment, or if he wasn't planning on it before, he certainly is now. And so we'll cover a whole range of advanced format specifiers, but if you want to find out all the different ways that you can format numbers, there are a couple of resources. So number one is just the plain man pages. If we go scroll down on the man page for printf, so you can see a minus sign specifies the left adjustment of the output in the indicated field. And a 0 indicates that 0 padding should be used. You can experiment with all of these in the man pages. We'll also provide a link to a simplified man pages. The book has the details of a whole lot of different format specifiers, and you can also just try it out. So we encourage you to play around with these format specifiers, and you'll learn how to format your output from your loops in a visually pleasing way. To print hashes instead of white space for the alignment characters? I'm not actually sure. You can certainly do it programmatically. I don't think you can do it using a format specifier, but printf is such a complex function that I don't know all the ins and outs of it, and I don't know all the format specifiers off of the top of my head. So if I were going to try and answer that question, there are two things I'd do. I'd Google it and look up Stack Overflow, and then if that didn't help, I would look through the man pages. And then if that still failed, I'd probably write my own solution. Which is one of the beautiful things about programming, is if all else fails, you can actually go yourself and solve the problem. Okay, so now we've done a whole bunch of fancy printing, we've done some iteration, but we haven't actually done anything useful. So it's time to see what we can do with our tools. This is a program called savings.c that should help you out a little bit with your income. This is our first program that has more than just a small number of lines, excluding the day number 1, which was mostly the same kind of thing. This is performing actually a useful function. You'll see we have a few different hash defines up the top. This indicates a very expressive and useful way of using hash defines, because these are numbers which, while constant for a given run of the code, might actually change over the course of your life. So for example, your monthly savings amount might be $100 a month now, but hopefully in a few years, once you've all finished this course, you'll be making $300K at Google, and hopefully you'll be able to bump up that savings number a little bit. So we have the interest rate that we expect to potentially be getting at the lower end, and I think this number is actually a little bit off, given the way that interest rates are at the moment. And what's a reasonable interest rate upper bound? What do we think it'll get up to? 0? Hopefully not. Unless any of you have a home loan, which would be impressive at this point. But let's say that the maximum interest rate we could expect would be maybe 4%. And that's very wishful thinking. But leave it there anyway. Maybe our term deposits will all do well. So what we want to do And what it looks like this program is doing from just the hash defines, from not even reading the rest of the code, is we're going to contribute some monthly amount into a savings account, and we are going to have different interest rates, and we want to look at what will happen to our savings over a period of time if we constantly contribute and if we get paid out interest at a certain rate. So in this case, interest rates are annual, and we are compounding monthly. So we figure out what the effective interest rate is for a given month. So that's the annual interest rate divided by 12. We apply it to the amount that's currently in the account. So if the amount in the account is $100 and there is a 2% interest rate accounting for a 2% effective monthly interest rate, after a month would have $102. Now obviously 2% a month would be gloriously beyond many of our wildest dreams, but that was just for illustration. Okay, so let's look at how we actually do this. We start the interest rates at the minimum and start at the maximum, and it looks like we're just printing out what the possible interest rates are. And our comment here says print the table heading lines. So it sounds like what we're going to be doing is printing a whole table of what you'd make for each different interest rate. So we print the heading, we print each of the possible different interest rates, noting that we're using some of our format specifiers to align the table nicely. And now we print each row of the table. So this will be what our savings will be for each different value of the interest rate. And for each number of years up to max years. So each line will start with, after X number of years, or after year number of years, then we have another internal loop that'll calculate the amount we'd have for each year for each different interest rate. Let's assume we have 0 savings to begin with, figure out the monthly interest rate that's going to be applied, and then for each month, perform our actual compounding. Now, those of you who've done maybe a little bit of personal finance know that there's actually a closed form solution to this. You don't need to run it in the loop. But this is more to show you the power of iteration and how you can solve problems even if you don't know the fancy closed form solution. So at each month, we're going to update our monthly balance by multiplying it by the effective monthly interest rate. And then figuring out how much interest we get, we're going to add that to our balance and our monthly savings. That's where the interest is added, and this is where our monthly savings are added. And then just print the balance after all the years have run through. After we get to the end of a row, we're again going to print a new line, and that will give us the next entry in the table. So let's run this and see if it works. And fortunately, we're past some of the tricks, so we're on to working programs. So you can see here the application of all of the different loops. We have our first loop that did the table heading over here, 1%, 2%, 3%, 4%. And then for each year is a row, and after each row we print a new line. And within that, we're going to run the calculation starting from year 0 up to the maximum number of years, calculating for each month how much gets added at each month. What you see here is a more sophisticated example of structuring a program that has loops within loops. Next week, we're going to see how to use functions to abstract this out even further, because having so many nested loops isn't necessarily an easy way of thinking about this problem. It would have been much easier if we could divide it up into, say, figuring out how do I figure out how much interest gets added to my account in a year? How do I figure out how to print the rows of a table, assuming that I know what the value of the rows are? So by chunking this up into different segments, we can make our lives as programmers easier and also hopefully have fewer bugs in our code. Okay, the next example illustrates something that I spoke about last week, and that's that C is whitespace independent. So this is the same as our day number program that printed what day we're up to in the year, only it's all squished together without whitespace. As you might expect, this does compile and run. Take this the 9th. So it works perfectly fine, but if we see this in your project code, you are probably getting a 0 on style. So I highly recommend not to go down that path unless you're participating in one of the Obfuscated C competitions where the goal is to write code that is as difficult to parse as possible. While we're at it, we're doing well on time, so I think we can actually afford to look at one of these competitions very briefly. If only Zoom wasn't obscuring the navigation bar. Here we go. So this is an example here of Hello World. It does actually run correctly, but a little surprising. In order to actually figure out what it's doing, if you start adding spaces, you can figure out a little more. But again, remember, this code was designed to be as hard to read as possible. Let's see if I can show another example, something more sophisticated. So there's actually an annual competition to write the worst possible C code you can. See what this one does. So here, I think this one prints out some of the script of Star Wars, but I can't actually tell. Shall we run it and see what happens? I highly recommend not making a habit of running C that you pick up on strange places on the internet. But just for fun, we'll see. Oops. That was a mistake. It'll still run. IOCC is the International Obfuscated C competition. So that should give you some sense of what not to do unless you know what you're doing, in which case, go ahead and do it. Okay, for maybe one of our last examples, we have a program called 3n.c. And I've got some information about what this program does at the top because it's a little more complicated. So the 3n conjecture is a mathematical conjecture that says if you perform these certain steps from a positive integer, will you eventually get back to 1? So the steps are, if the previous term is even, if the previous term is even, the next term is half of what you're currently at. If the term is odd, multiply it by 3 and add 1. The conjecture is that these processes, if you do this for any input number starting in any place, you're always going to get back to 1. So the goal of this program is to see if this is true and giving us, well, maybe we can't prove it, but perhaps we can play around with at least some examples. So first off, it asks us for a starting value. So what number do we want to try this with starting at? And over here we've got our checking. This is a good example of checking to see if scanf succeeded. And if it didn't succeed for some reason, report a failure. Once a value of n has been read, set the maximum value that we've reached so far. So one of the things that we'll keep track of is what is the highest value that we've seen in this process. We're going to count how many times we've gone and done this up and down thing. So that's our cycles value. And then we have a while loop. So mostly in this lecture, we've only discussed for loops. While loops are just a simpler version that only has a condition and a body. The condition is checked, then we run the body, then we go back to the condition, then we go back to the body. Again, the same rule applies that the body should change, should make some progress towards completing the condition, otherwise you get an infinite loop. So print out what our current number is. If the number is even, halve it. If the number is odd, multiply it by 3 and add 1. If the number that we get as a result is larger than the biggest number we've seen so far, save it, and so we know that it's the new biggest number, and then count the number of cycles we're up to. And then this is just for printing new lines. Then when we get back to 1, report how many cycles were consumed and what the maximum value we obtained was. Let's give it a run. What number should I put in? 200, okay. So we can see that 200 got halved to 100, that got halved to 50, that got halved to 25, multiplied by 3 to 75, add 1. That's even, halve it. That is even, halve it. That's odd, multiplied by 3, add 1, etc., etc. You can see that for 200, it took 26 cycles, and the maximum value was in fact 200 that we started with. Let's try it with a different number. 42. In this case, the maximum is actually larger than the value we entered. What about with a bigger number? Let's try. So even with a pretty big number, this still only takes 177 cycles to get back to 1. Now we don't actually know whether this conjecture is true or not. I encourage you to try to prove it if you want, but be aware that you might be waiting a long time and that this is certainly out of bounds of the course. In fact, if you do manage to prove the conjecture one way or another, I'm sure we could work out some way to factor that into your grade for the class. But I might end up in some trouble with the handbook, but we could make it work. Maybe at least award you a PhD. But if you're looking for time efficiency of studying, that's probably not the way to go. And I think with that, we're at time for class. We have 2 more programs to look at from our large set of examples, and then we're going to get on to a little more advanced material and things that are actually new fundamentally about C from Python. So I hope you're all looking forward to that, and I will see you tomorrow. Thank you very much, everyone.